Aloha. In this video, I'd like to look at two solutions for which either the problem was written erroneously in your book, or the person who wrote the solutions for the publisher made a mistake. These problems do crop up occasionally. One of your classmates caught these. The first one is number 39, about a Carnot refrigerator. Remember Carnot? He was one of the first physicists who looked at thermodynamics, or advanced the field. And so there's this ideal PV cycle, this ideal heat engine that's named after him. It's a reversible cycle. It's the most efficient possible heat engine. And that's the sort of cycle that we're supposed to imagine here. But this particular engine is being run in reverse as a refrigerator. I hope you've read about that in the chapter. Here's the heat diagram for the refrigerator. Now remember, this little schematic here doesn't show you anything about the technical details of the heat engine. It doesn't even have a picture of the working substance, whether it's a gas or steam is a gas. It's purely, the only information it contains is the relative quantities, or how much work you have to put in compared to the heat. Like the thickness of the bars here is what has some significance, but there's no numbers. And it shows you the direction in which energy flows. Okay, so the word refrigerator doesn't have to mean a refrigerator in your kitchen for keeping food cold, but you can think about it that way for this problem if you'd like. So if this is a kitchen refrigerator, the so-called cold reservoir, that would be the air inside the refrigerator. And they're telling us that the temperature is -20 degrees Celsius, which sounds pretty cold actually, because 0 degrees is freezing, which means we're actually talking about a freezer. Colloquially we call it a freezer, but in the thermodynamics language we call it still a refrigerator. So the inside air inside this freezer, -20 degrees Celsius. And the hot reservoir in this case is the air inside the kitchen, not the air inside the refrigerator. It's the room temperature air. Now that's not really what we think of as hot, but we have to distinguish the higher temperature from the lower temperature. So we just call it the hot reservoir and the cold reservoir. And in this case, the hot reservoir has temperature of 25 degrees Celsius. So that's kind of a warm room. It's certainly not hot in the normal sense. So 25 up here, -20 down here. Those are the so-called reservoirs. Now where your book messes up is they say that the hot reservoir is actually 50 degrees Celsius. And that's definitely an error, and it threw me off for a second. I had to think about it. If you've read about refrigerators, you understand that the working substance, what we would call the refrigerant, it used to be Freon, now it's some other kind of refrigerant. It's a fluid inside those coils within the refrigerator, and that fluid gets circulated. There's something in there called a condenser and a compressor. I forget the details. Sometimes the fluid is in the gaseous form. Other times it's more of a liquid. That fluid is going to, at some point in its cycle, it's going to get very hot. It's going to be up at 50 degrees Celsius. Because remember, in order to dump heat, the whole idea is that fluid is going to draw heat from the cold reservoir, that's the air inside the freezer, and dump it to the outside. Those coils on the back of your fridge or the bottom of your fridge, that's where that heat gets exchanged. And remember the second law of thermodynamics, heat always flows spontaneously from hot to cold, never the other way around. So the only way that the working substance, that fluid within the coils, the only way it's going to dump heat to the outside air in the kitchen is if the working substance is at a higher temperature than the room. So the room is at 25 degrees Celsius. This is the air in the room. The working substance, which is not shown in this diagram, would have to be at an even higher temperature. That's the 50 degrees Celsius. So the temperature of the reservoir, that is not the temperature of the working substance. The temperature of the reservoir is the temperature of the air in the room. And that's what your problem goofed. And that, the fact that happened should give you some encouragement. This is not always easy to think about. The math in this chapter is not difficult. We're not doing any fancy calculus. There's that one integral with the natural log for an isothermal process. But aside from that, there's very little math here. It's conceptually that it's challenging. Some of the stuff you probably never thought of before. In fact, quick anecdote, I went to school with somebody who ended up getting a PhD in mathematics at Cornell University, really smart guy. And we were conversing one day about some of this basic stuff in thermodynamics, and he was under the impression that you could invent a device that would suck heat out of your room without having to dump it outside, like an air conditioner, some sort of air conditioning machine that doesn't have to vent to the outside. And that made me laugh immediately because I had spent a lot of time thinking about this stuff for these classes, and the heat's got to go somewhere. There's got to be a hot reservoir, and it can't be within your room because then you're just heating your room up. You can't store the heat in pellets. I mean, I suppose that's conceivable because you could lock energy up as mass, but that would have to be like a nuclear process. So the point is that this stuff is not obvious. Okay, so first we'll establish 20 degrees, negative 20 is the cold reservoir, and room temperature is positive 25 degrees. Yes, the working substance gets up to 50, but that's not the hot reservoir temperature. Okay, then what they tell us, by the way, the heat doesn't spontaneously go from inside your fridge to the outside, right? That would be a violation of the second law. That's why you have to put work into the system to get that to happen. There must be an input of work. This is the electrical energy. If we're talking about your freezer, this is the electrical energy that you pay for from the power plant. It's you've got the thing plugged into the wall, and that's where the work in is coming from. Yes, the actual work is being done by the compressor or the condenser. I forget which one, but we're not concerned with the details. This is not an engineering class. This is just the basic thermodynamics that we're looking at. Now, as far as describing the efficiency of a refrigerator, we do it a little bit differently than we do it for heat engines. The idea, the motivation for these definitions is always kind of common sense. If you're designing a freezer, what's the whole point of the freezer? You want to scoop heat out of the freezer and dump it outside because due to conduction, there's always a tendency for heat to leak into the freezer through the walls of the freezer, and you want to scoop that back out. So you want to scoop out as much possible heat for as little money as you can. So QC, that's the heat that is drawn up from the cold reservoir. This is the whole point. You want to scoop as much of this heat out of the freezer as you can to keep it cold. So that's what they're saying. That's what they're referring to as what you get. I'm doing the air quotes here. QC, you'd like that to be as large of a quantity as possible, but you don't want to have to pay a lot for it. Remember, you get billed per kilowatt hour by the power company. You pay 15 cents or whatever per kilowatt hour. It would be nice if you could just pay for 1 kilowatt hour and your machine is so efficient that you scoop out, 50 megajoules of heat. I don't know what the actual number is, but so you want the numerator to be as large as possible and the denominator to be as small as possible. They're using the letter K for the coefficient of performance. I think it's often abbreviated COP in manuals. If you pick up a manual for a refrigerator or the technical specifications, they'll probably call it COP, coefficient of performance. So it's like efficiency, but it's technically a different definition. You should go back and look at the definition of efficiency for a heat engine. Okay, so this is the definition of coefficient of performance, regardless of which PV cycle you're using. No matter how the refrigerator works, that's the definition of coefficient of performance. But if you read in the book, there's a particular coefficient of performance for a Carnot cycle. A Carnot or reversible cycle. I'll try to put up a video where we talk about what it means for something to be reversible in the thermodynamic sense, not like your raincoat. For that cycle, that's the upper limit on coefficient of performance. No refrigerator can exceed the coefficient of performance of a reversible cycle. And here it is. It's merely the difference, it's the temperature of the cold reservoir, that's an absolute temperature, divided by the difference in the temperatures. Not an obvious result at all. And your book actually does not derive that result. They derive a similar result for heat engines, and they say, refer to a homework problem or work it out for yourself. So this result is just quoted, but this is the greatest possible coefficient of performance that you could achieve with the refrigerator. And notice that it depends on the two temperatures. And if we look at the denominator here, how would you increase coefficient of performance? You would need the denominator to be smaller and the numerator to be bigger. Well, let's just focus on the denominator. The closer these two temperatures are, the smaller the denominator is. I mean, if these were equal, the denominator would be 0. So the closer these are, the greater the coefficient of performance. And that tells us that your refrigerator will actually be more efficient on a day when your kitchen air temperature is close to the temperature within the refrigerator. So, actually we're talking about a freezer here. If it was a cold winter day and you didn't turn on the heat for the entire house and you let your kitchen get really cold, your freezer would actually have an easier time scooping energy out. And it's not just because, well, maybe you're aware that heat flows faster when there's a greater temperature difference. That's that conduction equation that we've looked at. It's really a different statement from that. Let me see if I can put it in simple terms. This, again, I'm just pulling this ratio out of thin air, but suppose that on a hot day when your kitchen is really warm, suppose you have to spend $1 to scoop out 1 megajoule of heat from your freezer. On a cold day when your kitchen air temperature is closer to the desired temperature inside your freezer, you may only have to spend 60 cents to scoop out that same 1 megajoule. So it takes less work input per megajoule of heat when the temperature difference is smaller. And maybe that's not intuitive. I don't think it's really intuitive for me. Same thing is true of your air conditioner. If you want your room to be at 72 degrees Fahrenheit and it's 110 degrees outside because you live in the desert, it's going to cost you a lot of energy. Excuse me, it's going to cost you a lot of money per megajoule of heat that you scoop out of your house. Whereas if you wanted to keep your home at 72 degrees and the outside was only 75 degrees, it's going to cost you less energy per megajoule that you scoop out of your house. Right? That's just a consequence of this analysis that comes from thermodynamics. Okay, so let's write down what the book gave us. They told us that the two reservoir temperatures were, well, for the cold temperature reservoir, we're told that it's negative 20 degrees. And then they said that the hot temperature reservoir was 50 degrees Celsius. That's bogus. I believe they're referring to the highest temperature achieved by the working substance. The hot reservoir is the room air. And that's not going to be 50 degrees Celsius. That's ridiculous. It's only 25 degrees Celsius. So we can easily convert these into absolute temperatures, add 273. So for the cold, what is that, 253? And then the difference between these two, no need to convert, looks like 45. So 353 kelvins. I'm not going to put the K because that'll be confusing. We're using K for coefficient of performance. What is the maximum possible efficiency here? 253 divided by 45. Well, that would be 5.62. What does that mean? Well, just a moment ago, you saw the definition of coefficient of performance in the book. It's, in general, remember, this is only applicable for a Carnot refrigerator, the idealized cycle. But in general, for any refrigerator, it's how much heat you can scoop out of your freezer compared to what you had to pay for from the power company. So now that we know what the maximum is, we can figure out, let's see, what are they asking? Yeah, what electric power does the freezer require to maintain that inside temperature? Okay, well, here's the other, we're going to come back to that. Here's the other information we need. We're given the dimensions of this freezer box. It's a cube. And that cube is 40 centimeters on a side. And, you know, a cube's got 6 sides. Go ahead, count them. And we're told that all but one of them is a perfect insulator. So I'll say perfect insulator. Same thing up top. And with all the other sides, I won't label those. But this one side, for whatever reason, they left it as just a slab of stainless steel. And stainless steel conducts pretty well, right? It conducts heat pretty well. That's not going to keep the heat out and the cold in, so to speak. We know that heat will be transferred through the stainless steel from the warm air of your kitchen into the interior of the freezer. And that's the heat that we have to scoop out. The whole point of the freezer is to offset that inward flow of heat due to the temperature difference. Heat's flowing in via conduction. We got to keep scooping it out using the refrigerant within the coils inside the freezer box. So this is a problem in conduction. So I'll say rate of conduction. This is one of the formulas from the previous chapter. It's going to be proportional to the surface area of that slab of stainless steel. It's also going to be inversely proportional to the thickness. And in the previous chapter, we used L. So I haven't written the thickness down, but I'll do that in a moment. Here's your stainless steel slab. And it's also proportional to the temperature difference. Remember, I compared this to Ohm's law. Okay, so these numbers are given. We're told that the thickness here is 1 centimeter. The stainless steel door is 1 centimeter thick. So we plug that in here. We take 40 centimeters by 40 centimeters for the area, and we just take the difference in the reservoir temperatures. We've got 25 outside and negative 20 inside. That will be delta T. The only thing we need is the conductivity of stainless steel, and that's something that you would either be given or you would look it up in a table. I'm just going to quote the number from the book. So for stainless steel, we'll go with a conductivity of 14 watts per meter Kelvin. Do you need to know those units? No, I don't know them. I'd have to look the formula to get those units. Okay, so how many joules are being conducted into the interior of the freezer box every second? Because that's how many we have to scoop out every second. So we take the 14 watts per meter Kelvin, and then I'm not going to include all the units here, but the area will be 40 centimeters. That's 0.4 meters, 0.40 meters. I square that because we're looking at a square. The area would just be 40 centimeters times 40 centimeters. And then the thickness here, which is what the book calls L, that's the 1 centimeter, so 0.01. Notice I'm putting all the numbers in SI. I believe this is coffee. Don't get grossed out. And then delta T here, well, we know that the temperature difference was 45. Okay, so let's see how many joules are leaking through this stainless steel door every second. Oh, that can't be right. Can it? 10,080 joules every second. 10 kilowatts? That can't be right, because if you want to scoop out 10,000 joules every second, it seems like you might need a 10 kilowatt pump, so to speak. And that's, even a microwave oven is only about 1 kilowatt. This sounds really expensive. Nope, that's the number. I'm looking at the solutions manual. That is the correct number. Okay, so what is this telling us immediately? This is a really stupid design for a freezer. Why would you design a freezer that's so poorly insulated that 10 kilowatts of heat are leaking through? You're gonna have to scoop that back out. So the number one thing you wanna do is increase the insulation. And you know what this reminds me of? I have a friend whose family has a small house in Ontario, and again, not a big house. Their AC bill, the electric bill during the summer, should not be astronomical, but they pay like $600 a month for air conditioning during the summer months. And that means either their air conditioning unit is really inefficient, which is not the case because they recently bought a new one, or it means that their house is really poorly insulated, so that during the summer, the heat's just, again, you could think of this as a freezer box, or you could think of this as an actual home that you're trying to keep cool, despite the fact that the air outside is hot. So you got to fix the insulation first, prevent conduction. Okay, 10,080 joules per second. Well, let's just focus on the numerator. Let's look at this problem on a per second basis. every second, that's the amount of heat that flows through the stainless steel door. And we need to scoop that back out in order to maintain that low temperature reservoir at negative 20 degrees Celsius. So we go back up to here now. And we've now determined QC. Let me pause and go back to the graphic. Look back at the energy diagram, I'm going to call it, for, your book has another name for it, for the refrigerator. QC, that's the 10,080 joules. I'll call it 10 kilojoules that we need to scoop out. This picture does not show you the conduction into the freezer box. That's not part of this graphic here. We need to scoop those 10,000 joules back out. That's QC. Well, how much energy are we going to have to pay for from the power company to get that to happen? Because it's not going to happen by itself. If you chop off, can you see my arrow? If you chop off this part of the diagram, you would just have a bar going from here to there. That would be spontaneous flow of heat from cold reservoir to hot reservoir. That doesn't happen, right? That's a violation of the second law of thermodynamics. You have to put energy in to get this to happen. And it would be nice if you could just put in like 1 joule of energy to scoop out 10,000 joules, but we know that's impossible because that would exceed the Carnot coefficient of performance. So let's figure out how much energy we have to pay for from the power company to get this transfer to happen. That means solving this equation for the work in, the input work. So work in would be QC over coefficient of performance. But luckily, we're told that our particular freezer is a Carnot freezer. Of course, that's silly. You can't buy that anywhere. That's just a theoretical ideal. Work input would be QC over coefficient of performance. And remember, I'm looking at this on a per second basis. Every second, how much heat do you have to scoop out, and how much energy consequently will you have to pay for from the power company? So take that 10,080 joules and divide it by the maximum possible coefficient of performance, which would only be achieved by a reversible engine. We already calculated that. That's the 5.62. And I believe this is where your book may have goofed up. I don't know. Doesn't matter. We're doing it right. Okay, so for every 10,080 joules that you want to scoop out of the freezer box, you're going to have to pay for 192 joules of electrical energy from the power company. Yeah, and your book's not getting this same answer, so let me pause. Yes, they're getting a different answer because they used 50 degrees Celsius for the high temperature reservoir. And I think that's dumb. I really hope I'm not making a mistake here, but I'm like 99.999% sure that that was an error on their part. Okay, so that's pretty cool, right? You only have to pay for 192 joules and you get to scoop out over 10,000 joules. But you're not going to get that kind of efficiency with an actual refrigerator. This is the theoretical maximum. Now, what they actually ask for is not the energy in 1 second. They ask for the power. And, well, that's really kind of the same thing because power is the energy that you have to draw from the power company per unit time. And that's kind of what we've done here because I just calculated how much work is required for every 1 second. And we found that that's 192 joules. And there it is. A joule per second is a watt. What is that? It is a watt. 192 watts. That sounds about right. Your book's answer, 2.8 kilowatts? I mean, that's just, that can't be right. Okay. Book made a mistake, and I just made a mistake too. I think I dropped a 0. Let's try that again. 10,080 divided by 5.62. There we go. Okay, so that's more like 1.79 kilojoules. That sounds more reasonable. Almost 2 kilojoules are required from the power company to scoop out the 10 kilojoules of heat from the freezer box. So this number should be a little different, and I'll just skip straight to 1.79 kilowatts. Now, that's a lot of power draw for a freezer. You can, if you have a refrigerator in your home, go open up the door, see if you can get the specs, or just Google it. Most refrigerators do not draw this kind of power, because that would really add up. That's like running a toaster oven all day, every day, because your refrigerator is running often. And why is that? Well, that's because this freezer box is terrible. It's extremely leaky. So again, you'd have to fix the insulation there. But contrast this with your book's answer. They have 2.8 kilowatts, and that's because they mistakenly used 50 degrees as the high temperature reservoir. So the problem isn't just with the solution here, it's also with whoever wrote the problem. This next problem that I want to look at, number 48, is also simple mathematically, but a little challenging conceptually. It's also about a refrigerator, which is a heat engine being run in reverse. Again, the heat engine, normally the heat QH is drawn off of the hot reservoir, and there's a work output. So this arrow gets reversed, and then there's a waste heat dumped back into the cold reservoir. So every one of these arrows would be reversed. That's usually what we're looking at. That's a heat engine. This is a heat engine in reverse, which is what we normally call a refrigerator. But sometimes it goes by a different name, and that's what this problem is about. So in the previous problem, the whole purpose was to keep the refrigerator cold at the expense of warming the air in the kitchen. That's the objective, to keep this cold. But what if your objective was not to keep the cold reservoir cold, but to keep the hot reservoir warm? What if that's what was desired? And that's exactly the case during the winter. It's a little bizarre because we flipped it inside out, but the cold reservoir is now the exterior of your home. It's the cold air outside, and the hot reservoir is inside your home. And you would like to draw heat out of the cold air in the exterior of your home and put it back into your home. So you're sucking heat out of the cold air and putting it in your house, which is not very intuitive, right? Because normally you think of heat flowing from hot to cold. You would expect that your warm house would leak heat to the outside. And it's not your first impulse to think that, oh, you can take heat out of the winter air. Like, it doesn't seem like the winter air has any heat that you can draw from, but it does. There's quite a bit of thermal energy, even at 0 degree temperature. So even though it really is a refrigerator, it's still operating as a refrigerator. We call this a heat pump to signify that the purpose is different. The objective here is to keep this warm, not to keep this cold. We don't care about having any particular temperature for the outdoors. That's the outdoors. We care about the temperature inside the home. So it is a refrigerator, but because of that slightly different purpose, it's called a heat pump. That's what the problem's about. Now, because of the different purpose, your book introduces a slightly different definition for the coefficient of performance. And this is where the mistake comes in on the part of the solutions manual. If you read the problem in the book, they give a new definition for the coefficient of a heat pump. But then the person who wrote the solution disregards that definition and continues with the original definition. Again, here's the original definition, because the whole point is to scoop as much heat as possible out of the cold reservoir in your freezer box. That's why this is a sensible definition for an actual food refrigerator or freezer. But now the objective is different. The whole point now is to scoop as much heat as possible into the hot reservoir, which is your home. So let's modify the definition of coefficient of performance for a heat pump versus a refrigerator. And if we just go with the common sense definition of coefficient of performance for a heat pump, you want to get as much as possible for what you pay for. Well, what is the desired quantity? You want to pump as much heat as possible into the hot reservoir. That's your home. But you have to pay for that. And we need a relationship between these two. So I'm going to pause and go back to the original diagram for a heat engine, rather than talking about a heat engine run in reverse, which is what this problem is about. Let's just look at the original diagram for the heat engine. You draw a certain quantity of heat out of the hot reservoir, and as much of that as possible, you'd like to go into useful output work. Some of it gets wasted as heat. I think the best example to think of is just an automobile. when you ignite the gasoline air mixture within the cylinders of your engine, you introduce a whole bunch of heat into the system. It was originally locked up in the chemical bonds of the petroleum products. And the useful output work is your car moving forward. It's the gears turning, the wheels turning. But of course, there's going to be some waste heat. In fact, most of it is waste heat. It comes out your exhaust pipe, where it's just dissipated thermally in the manifold and in the air near the engine. So if you just think of this diagram, you can always remember the following. That heat that comes off the hot reservoir gets split between useful output work and waste heat. It's true for a heat engine, but it's also true for a heat engine in reverse, which is sometimes called a refrigerator, sometimes called a heat pump. That's what this problem is about. Of course, in that context, we would call this input work instead. So it's a very simple relationship, but you just take, think about your freezer box, back to the previous problem. If you scoop out 100 joules from the freezer, and to do that, you had to pay for 20 joules from the power company, a total of 120 joules is actually being dumped into your kitchen. Did you know that the electrical energy that you're drawing from the power company with your refrigerator is actually being dissipated thermally within your room? So the kitchen does tend to rise, the temperature tends to rise a little bit due to the use of your refrigerator. You cannot cool your kitchen by just plugging your refrigerator in and leaving the door open. The only thing that's going to do is actually heat your room up, or heat your kitchen up. You know, what the problem tells us is that the particular heat pump used by this homeowner has a coefficient of performance of 5. And here's where the person who wrote the solutions manual goofed up. They plugged in QC here. They were going with the definition of coefficient of performance for a refrigerator whose purpose is to keep the cold reservoir cold. We're talking about a heat pump with a different objective. They really should have used this definition for coefficient of performance. And it does affect the results slightly. So if I solve this for Wn will be QH over K. That's K for coefficient of performance. And that's QH over 5 for this particular problem. And what they're asking us to do is contrast the power needs of a homeowner using this heat pump in the winter versus a homeowner who just uses like heating coils, space heaters. I'm sure a lot of you have one of these at home. It's basically like a big toaster. You plug it into the electrical outlet, and there's some metal coils that get really hot, and they radiate mostly infrared, but some red light into your room. And that's a 100% conversion of electrical energy into thermal energy, which is kind of cool if you think about it. A toaster, in that sense, is really efficient. You know, if your toaster draws 1 kilowatt, that means every second 1,000 joules of electrical energy are going directly into heat. Now, how much of that heat makes its way into your bread, that's another matter, but at least it's going into your room. So let me draw a silly picture here. If this is your house, and here's the electrical wires coming from the power company, and your space heater is basically, it's like the filament of a light bulb, it's just much bigger. It's just a coil of wire, and electromagnetic waves, mostly infrared, are radiating from that. And this will be absorbed by the air in the room, or the walls, the furniture, your body, hopefully your body. That's usually how you position the space heater. And so you might think that's as good as you can get, but check it out with a heat pump. Let's see here. Yeah, let's say you want to dump 1,000 joules of energy into your room. The work input, which is the energy you pay for from the power company, only needs to be 1,000 divided by 5, or in other words, 200 joules. So you're only paying for 200 joules, and yet you get 1,000 joules of heat pumped into your house. That almost seems too good to be true, because with the space heater, if you want 1,000 joules of energy pumped into your home, you're gonna have to pay for 1,000 joules. So theoretically, this should cost 5 times less. using a heat pump compared to just direct heating with hot coils. So again, it seems a little counterintuitive. It seems like you're getting something for nothing, but you're not. You're not creating energy. You're just assisting its flow. So let's just stick with the numbers I've been using, 200, 1,000, since the coefficient of performance is 5. You pay for 200 joules of energy from the power company, and that induces the working substance of your heat pump here to transfer an additional 800 joules of energy from the air outside your home into the air inside your home. So there's a total of 1,000 joules. Only 200 joules do you have to pay for from the power company. That's a lot better than just paying for 200 joules and having just the 200 joules dissipated with the heating coils. Now, the actual number that the problem gives us to work with is 15 kilowatts. That sounds reasonable. If you've got a decent sized home and it's really cold in the middle of February and you need to keep your house warm, perhaps you need to draw power at a rate, or you need to dump 15,000 joules of heat into your home every second to compensate for the fact that it's being conducted out through the windows, through cracks in the drywall, you know, wherever the heat is leaking out. Okay, for the heat pump, every second. Well, this is the number of joules per second. So in 1 second, the heat that would need to be dumped into your home is 15,000 joules, 15 kilojoules. But the only amount of energy that you have to pay for from the power company comes from here. I'm going to take those 15 kilojoules and divide it down by the coefficient of performance, and that's only 3 kilojoules. And this is where your solutions manual goofed up. They found that you'd only have to use 2.5 kilojoules. And that is because they used the wrong definition for the coefficient of performance. They went with the one that would be appropriate for a refrigerator, where the purpose is to keep the cold reservoir cold. And let's see here. If this is the definition they used, I'm going to use this relationship between the three. QC would be QH minus input work. Well, that would be the required 15 kilowatts minus, or 15 kilojoules minus the 3 kilojoules. 15 minus 3 is 12. So QC would be 12. 12 divided by the work input of 3 would be 4. So did they get it? Hang on a second. Okay, I see what they did. It is, I would say, wrong what they did. They didn't take the wording of the problem literally. Here's where your solutions manual went awry. They stuck with this definition of coefficient of performance, which would be appropriate if you were just trying to keep the cold reservoir cold, like in a food refrigerator. And they said that means that the amount of heat drawn from the outside, the cold air, would be K times the input work. And then because the problem stated that the coefficient of performance of this heat pump was 5, they went ahead and said QC is 5 times work input. And then they recognized that the total heat dumped into the house is whatever power or energy you're drawing from the power company plus the heat that you sucked in from the cold air. And that would be work input plus the 5 work input for a total of 6 times the work input. And then they reintroduced the definition of coefficient of performance. They said, well, that means that the work input is going to be the total heat dumped into the house divided by 6. And so they said, if you need to put 15 kilojoules into your home every second to keep it warm, to counteract conduction, 15 divided by 6 is only 2.5 kilojoules. That's where they got the 2.5. So they kind of, I know it seems like we're going around in circles here, but this is really, this ratio really defines the coefficient of performance for a heat pump. And the way your book defined in the problem coefficient of performance for a heat pump was this. And they said that this is 5. Does this make sense? The confusion here comes from the two slightly different definitions of coefficient of heat performance. So for an actual refrigerator where the purpose is to keep the cold reservoir cold, you would go with what you get over what you pay. But for a heat pump, which is still a heat engine in reverse, but for a different purpose, the coefficient of performance is what you get over what you pay. And really, it just depends how you want to define things. And different books may define things differently. In fact, here, same book, different people working on the same book defined it differently. The one thing that's not going to change from one book to the other is this relationship. This is just conservation of energy. And then those relationships about the limits on efficiency, the Carnot limit, which showed up in the previous problem. Okay, so that was part A of the problem. We already found that the input work per second is 3 kilojoules, so the input power would only have to be 3 kilojoules per second. In other words, 3 kilowatts. So if you have a heat pump, you only have to draw 3 kilowatts of power during the winter to deliver heat to your home at a rate of 15 kilowatts. That's assuming your heat pump has a coefficient of performance of 5, defined as we defined it. Now let's look at the actual cost. This part's pretty easy. Part B, and you can tell this problem is dated. Whoever wrote this did so years ago, and it hasn't been updated because inflation has made electricity more expensive, especially here in California, where everything is so efficient. So in part B, they give you a, pardon me, a typical price for electrical energy. They say, go with a cost, an average cost of 40 megajoules per dollar. Well, I'm gonna, instead of putting joules per dollar, I'm gonna say dollars per joules. $1 for every 40 megajoules. I normally think of the cost of electricity in terms of the number of cents per kilowatt hour. So let's convert this. I just happen to have this memorized. There are 3.6 megajoules for every 1 kilowatt hour. See how megajoules cancel? That's a fun word, megajoule. 3.6 divided by 40 is 0.09 dollars per kilowatt hour, 9 cents per kilowatt hour. Check your electric bill. If you pay your own electric bill, it's probably more like 15 cents per kilowatt hour, and it's going to get even more expensive here in California. I think they're going to raise the rates for tier 2. I think they're doubling it. So if you have an inefficient cooling system in your home, it's going to get real expensive. And my guess is they're doing that to pressure everybody into getting solar panels. You see, it's all a collusion between the state government and these shady solar companies. Not that I'm a conspiracy theorist. So let's figure out what it's going to cost each person. The homeowner who just uses space heaters during the winter, or the homeowner who drops some cash on a good heat pump. So for the heat pump home owner, they tell us that the average house has got their heater on for 200 hours during the month. Well, if I take 200 hours into 30 days, was it 200? I thought it was going to 250. Yeah, 250 hours. Divide that into 30 days, then that means we're running the heater for a little more than 8 hours per day. Sounds reasonable. What are we going to pay monthly to keep the home warm at this rate? Well, the total energy required would be, let's first do it for the guy or gal with the heat pump. That's 3 kilojoules per second times 3,600 seconds per hour times, we're told that they're running their heat pump for 250 hours every month. I ran out of space. 3 kilojoules times 3,600 seconds times 250 hours is 2.7, I'll put a couple zeros here, times 10 to the 6th kilojoules. Okay. Well, I'd like to convert that into megajoules because that's the ratio that we're given, or the units that we're working with. So I'm going to use 3 of these zeros to add these 3 zeros, right? 1,000 kilojoules is a megajoule. So that would be 2.7 times 10 to the 3rd megajoules times $1 in these like 1998 units here. $1 for every, how many megajoules was it? 40 megajoules. Let's see what it's going to cost in dollars every month with the heat pump. 2.7 thousand divided by 40. $67.50. And I believe your solutions manual got a different number. They got $45 because they screwed up with the definition of coefficient of performance. Now, do we need to go back and calculate the cost for the person that's just using space heaters, you know, metal coils? I don't think so, because we already know that they're going to spend they're going to use 5 times as much energy from the power company every second. So all we have to do is take this amount and multiply it by 5. They're going to spend almost $340. And hang on a second. Oh, yeah, there's another mistake in here. Again, you get your own numbers in Mastering Physics, so maybe this isn't an issue for you. But in the statement of the problem within the book, they tell us that you run the heat pump for 250 hours a day. And then in the solutions manual, they're using 200 hours, sorry, not per day, per month. I wish there were 200 hours in a day. 200 hours per month is used here. So there's mistakes all over the place. I'm sorry about that. Hopefully this clears it up for you.